That is to help you with the case study that we have for this workshop. I'll start with a simple example where you want to try and forecast sales as a function of time. In this case, that's going to be month. And I'm going to use the scatter chart, insert, and I'm going to use the scatter chart. And this basically represents the relationship between month, time, and sales. It's very simple to do. You just right click here and say add trend line, and down here you ask for displaying the equation and ask where. And if you have a Mac, you just right click and do the same thing. Go to the options, and in the options you can ask for these last two things to display the equation and ask where. So what does it mean? It basically says the following. Ask where says that this is a very good fit. The closer to 1 it is, the better it is. And the equation of the straight line, going back to maybe first or second year of high school, says in a reverse order that y equals minus 4.34 plus 4.87x. In simple words, when x is equal to 0, it's the intercept down here, when x is equal to 0, y is equal to minus 4.34. And every month our sales are going up on the average about 4.87 units, whether it's dollars in sales. So if you understand how to do it, now we can go and try and fit supply and demand curves. I'm going to select or just click on a single cell here and insert one of these charts. I'm going to use this one, doesn't make any difference. Now we can try and find the equation that fits the supply curve and the demand curve. So let's try with this one. The demand goes up. This is our supply. So we can right click and add a trend line. And again, ask for the last two things. Since there are 2 points, ask where is going to be 1. It's a perfect line. It basically says that y, the supply, is equal 810 plus 170x, meaning as you increase the price, your demand is going to go up by 170 units. And the same thing we can do about our demand curve. You can right click, add trend line, and ask for the last two things here, the ask where and the equation. Of course, ask where is equal to 1. We know that because it's only 2 points. And it says that y equals 1040 minus 40x. Let me just say it in simple words. Because we have 2 points, it's very easy to estimate the demand curve. And as the price increases, the demand decreases. Okay, so now let's try and see something more complicated. So we have determined from the past what the demand is going to be when the price is 1, 2, 3, and 4, and what the supply is going to be. And you're going to discover that in this case it's not a straight line, so you can just try the chart and find out that this is a little bit more of a realistic example of supply and demand. The only thing is, can I fit a demand or supply function? And again, because we have Excel, we can do the following. Let's try the demand, right click, add a trend line, and then we'll discover that when we ask for the equation, it assumes that it's a linear straight line, and ask where is not going to be 1. It's close to 1, but what you can do, you can try any one of these other examples. For example, exponential, and in this case you found out that r is equal to 1, so it's a perfect match. You can try the other ones as well and play with them to see which one could do it for you. But in this case, you found out that the exponential is a perfect match. So if you wanted to tell what would be your demand curve, you can say that y equals to 1524.2 times e natural log to the power of minus 0.421x. You can just plug in an Excel function, and if anybody tells you that the price is $2.50, you can just plug it in there and find out what the demand is going to be. The same thing holds for my supply curve. I can just add a trend line. Of course, the initial one gives you the linear, and R square is going to be less than 1. And you can try again and see the exponential. It's not there. Linear we know is bad. Logarithmic is not working. Polynomial is the one you want to use. So now you have the equation that really represents in high accuracy your supply curve. So this is the way to find out what the functions are for.
Again, this is the solution to the apartment building case study. If you look at the data, it's all in here. We have $4 million is our purchasing cost. 3% is the real estate taxes. Maintenance cost is $600 per apartment per month. We have 40 apartments in the building. The real estate tax growth rate is about 3% per year. Maintenance cost is going to grow 8% a year. The rental is going to increase 6% a year. 5 is the multiplication factor, which is the factor which is going to multiply the revenue of the last year, which is going to be the selling price of the apartment building. 10% is the interest rate we are using for our NPV. We are not sure what the rental rate is going to be. Actually, the rental rate is going to determine what would be the occupancy, which is we want to create this demand curve. So if you look at the numbers that we have here, if we rent for $2,400, our occupancy is going to be 65%. For $2,200, it's going to be 75%. For $2,000, 85%. So what we do, we can create a chart to get the relationship between the rent and the occupancy. So if we insert a scatter chart, we are going to get the relationship. If we right click and we add a trend line and ask for the last two things, we are going to get the equation and R. R is the coefficient of determination. Because it's a straight line, it's going to be a 1, which is wonderful. And now we know the relationship between the rental price and the occupancy. This is the demand curve. So we can use it here in the cell and say that it's equal to 1.85 plus 0.0005 times the rent, and then you're going to see, I made a mistake obviously, 1.85 minus, and what we get is 85%. And if the rental price is going to be, for example, $2,200, we expect it to be 75%. So this demand function is working. When you have the demand function working, you can create the rest of the values here. Real estate is 3%, and then it increases 3% a year. And you can drag it to the rest of the years. Maintenance cost is the $600 times the number of apartments times 12, and then there is an increase of about 8% a year. We can drag it to the right. And these are the total costs for every one of the 4 years. Then we have our revenue. The revenue is going to be the rent times the occupancy times 40. And then it increases by 6% every year, and we can drag it all the way to the right. So my cash flow for year 1 is at the total revenue minus the expenses, which makes it $380,400, and then we can do it for the other 4 years. And then don't forget the final selling price, which is 5 times the revenue. So these are my 4 cash flows for the next 4 years. And the NPV is 532,558. So the problem or the objective is to find what should we rent it for in order to maximize our NPV. And we have 2 different ways of doing it. One, we can get a table and say equal NPV and find out what would be the NPV for any one of these potential rents that we can decide upon. So we are going to go data, what if analysis, data table, and what is changing down here is the rent. I can change the format to make it look better. And if you look at it, you see that the highest NPV is when the rent is $1,850. Let's try and chart it again. Insert this chart, and you figure out, you see that for 8,850, our NPV is going to be $38,851. A different way of finding out what is the optimal solution is to go to Data, Solver. We are trying to maximize our NPV, maximize. The changing cell is the rent, and it's not linear, so if you have it set as linear, it's not going to work linear because we have the NPV function, which is not linear. And when you solve, you're going to get the same solution we just found out using the data table and the chart. Rent the apartments for $1,850 a year. Your occupancy based on your demand curve is 92.5%, and then you have the highest NPV. So this is the solution.
This workbook introduces the solver, which is an optimization tool in Excel. We're going to use in one of the options this solver in the case study that we have. So you want to see whether you have the solver in this area under your data ribbon, and the Mac should have it in this area under the data ribbon with the big question mark next to it. If you don't have it, you can go to File, Options, Add-ins. You'll find the solver add-in. You'll say Go, check it, and say OK. With the Mac, if you don't see it, you can go to the Tools menu. Under the add-ins, you can activate the solver. So now we have the solver here. Here is an example of a single variable, x. And we know that we have this formula that says that y equals x minus 5 squared plus 5. And what I did is I created that function here and tried different values of x from 0 to 10. And when I solved it, I have all these values. I can look at this range and see that the lowest value is 5. And when you use a chart, I used the scatter chart and created it, I found out that the minimum is somewhere here where x is equal to 5 and y, which is x minus 5 squared plus 5, is equal to 5. But what we want to do is we want the solver to find for us the minimum value. So I just chose one value here, 25, and what I want to do is I want to use the solver to find for me that minimum of 5. The way to do it is click on that objective function here, G3, and go to the solver and ask to minimize it. I already tried it before. You can either maximize, minimize, or make it equal to a certain value. And what you want to do is you want Excel to change for you this value to find that minimum x that minimizes y. Make sure that this is nonlinear because it's not a straight line. We have x minus 5 squared. And when you say solve, Excel is going to find for you the minimum without this effort of creating the entire chart. So you found out that the minimum value of y is 5 when x is equal to 5. And you can use it with one variable, two variables, five variables. I'm just going to show you one more example. And in the case study that we have, we are going to have a single variable. So just to show you one more complex example. Here we have z equals x minus 5 squared plus y minus 5 squared plus 5. And what you want to do is you want to find the x and the y that are going to minimize this value. We're going to use the solver, but to show you what would happen is if you have two values, let's say 3 and 4, and you can say here 1 and 1, and find out that the value is 37. Of course, what you can do is you can manually try all the different values. So what I did here is I created a data table where this is equal to the value that we have here. I can try, say, 3 and 3, and then the value is very high. I used 33. 3 and 3, and then you're going to see that it's 13. And what the data table is doing, it's trying all the different values. And if you look at it carefully, you'll find out that when x is equal to 5 and y is equal to 5, this is the minimum. You can try other things. You can, for example, select this range and use also under the home menu conditional formatting and use any of these things to see where the minimum is. It's also showing you that the minimum is 5. And you can do all kinds of things. You can also select the range, copy it, paste it again, and take off the intersection. If you take off the intersection, Excel knows how to use this as x, these values as y. Of course, we see it already that this is the minimum, but now if you don't have a value in the intersection, you can try one of these charts that I like to use, say the surface chart, maybe this one, and when you see it, it's going to be somewhere here with 5 and 5. But the purpose of this exercise is to show you how to use the solver to get the same value of 5 and 5 giving you 5. So you click on this objective function and you go to the data solver and you say that you want to minimize C3, and now we have two changing cells, these two. Make sure that it's nonlinear, and when you solve it, it's going to give you the same solution that I just showed you in a very elaborate way of getting. When you say OK, you'll find out that the minimum value is when x is equal to 5, y is equal to 5, and the equation is also equal to 5. So this is a more complicated example than the one we are going to use in the case study, but it's a good idea to be able to